let's go ahead and continue our conversation about talking about the different types of hyperbolas that we have in front of us. So we've just talked about the transverse axis and the conjugate axis. And we've talked about covertices, vertices, and foci, and all those fun things. We want to take a look at our pictures here in just a moment of what a hyperbola actually is. And let's go ahead and just focus on that for just a moment. So the hyperbola is composed of two different curves known as branches. And I hope you can see this on my board here, but the blue curves here are actually the hyperbola itself. It's composed of those two different branches. All this dashed line stuff, you need that in order to construct your hyperbola. And we'll talk about in the next section how to find that, those different dashed lines that we have. Okay? But as you can see, a horizontal hyperbola, the reason it's called horizontal is because our branches here open out horizontally away from one another. Okay, so that's why that one's horizontal. If I look at the vertical, which my blue branches are here and there, they open away from one another vertically in this case. And the horizontal versus the vertical depends on what your equation looks like to begin with. So let's focus on those two equations for just a moment. The horizontal equation is given right here, x minus h squared over a squared minus y minus k squared all over b squared is equal to 1. Now, if you take a look at your notes from yesterday when we talked about the horizontal ellipse, these, like the horizontal hyperbola and the ellipse, they're really similar to one another. If I change one sign here, if I make that a plus sign, now I've got an ellipse. Okay, so you've got to be paying attention very, very closely to your equations with what you might have, because you know me, at the end of the chapter, we're going to mix everything together, and it'll just say graph the conic section. You'll have to identify what it is. So make sure you're looking over those formulas and make sure you know them. Okay? But the difference between the horizontal hyperbola equation and the vertical, as you can see, is where x minus h being squared is and where y minus k being squared is. Okay? In the horizontal, we see that x is above a. Alrighty? And in the vertical, we see that y is above a. Okay? Now, the value of a with the ellipse, that was yesterday, is very easy to find. It's always the bigger one. Okay? You can't do that with the hyperbola. Okay? Here's how you can identify the value of a, though, when you're talking about a hyperbola. It is always associated with the positive section. Here's what I mean by that. If I look here, this part is positive, right? Because there's a positive sign here. Okay, and this part is negative. Well, I know, because this is the horizontal, that a is always positive. Alright, so the a is underneath the x in this case, so that's what makes this one horizontal. If I look here, the a value once again is positive, isn't it? Okay, so since a is positive, b is negative, and a is underneath y, that's what makes this one a vertical hyperbola. Okay, so locating the value of a and making sure it's positive, that's what you've got to look for here. Okay, let's go ahead and mark up our pictures here, and we'll talk about where A, B, and eventually C, how all these things are connected to one another. So from yesterday, we talked about the center, of course, is going to be HK. That's still true once again today. The center, however, go ahead and mark that. The center is not actually on your hyperbola. Okay, it's not on either one of your branches. It's kind of like the center of a circle. Okay, the center is not on the circle itself, but you use it to construct your circle. You use the center to construct your hyperbola that is here. All right, so from the center, we're going to move along the transverse axis. The main axis that we have here moves horizontally. So these 2 points that I have marked right here, those are going to be your vertices. So vertex 1 and vertex 2. And that, how do I find that? Well, I find the value of a, and that tells me how far I move left and how far I move right. So let's see if I can squeeze that in here. So that is the value of a, which makes it important. Okay, so as I move in the other axis, which is the conjugate axis, that's going to give me my co-vertices here. So this is co-vertex 1, and this is co-vertex 2. And how do I find out where those are located? Well, I found the value of b, and that tells me how far to move up or move down when I'm talking about my co-vertices. Okay, so a and b still doing the same thing like they did in the ellipse. All right. C, the value of C is still doing the same thing. It's still moving to the foci. Now the foci in this particular figure are here and there. And I hope you can see that on my board, okay? They're on the inside portion of your curves. And that will always be true with any conic figure that we look at. If we look at the ellipse from yesterday, they were always inside the curve. Okay? These are always inside the curve with the hyperbola. When we get to the parabola, the focus will be on the inside of the curve. Okay? So, the focus here, right there once again. Now, I'm going to erase this vertex here because this is important. The value of C is going to tell you how far away your center is to your foci and to the other foci. Okay? And I don't know if you can tell from my drawing there since there's so much going on, but the value of C is obviously larger than the value of A in this case. All right? Which means our equation that we have to use with the hyperbola here is different than what we used with the ellipse yesterday. Okay? So this equation, C squared equals A squared plus B squared, is useful when you're talking about a hyperbola only. Okay? Now, how do people remember that? I've had people tell me that that's the Pythagorean theorem, right? They say the hyperbola is related to the Pythagorean theorem, so that's how they know to use this equation. If that works for you, great. If it doesn't, just make sure you know that this equation only works for the hyperbola. And don't get that confused with the one I gave you yesterday for the ellipse. Alrighty? So, that's what your conic figure should look like here. Last thing that I want to talk to you about, and maybe I'll use this picture to help you see what is there. But with this figure here, I could go through and mark all my vertices, my co-vertices, and my foci once again. Maybe I'll do that real quick. So bear with me. Alright, remember the vertices always are connected to your branches. Your co-vertices are always opposite what is there. And your foci are always inside your curve. Cool. Here, I said that, Mr. Boyer. I know. Okay? It's weird I'm talking to myself on a video. So you have your diagonal lines here. How do I construct those? Well, you're going to construct your box here is what I call it. Okay? And then after you construct the box using your vertices, your co-vertices, and your foci, you're going to make these diagonal lines. Those are asymptotes, which we talked about that in chapter 7. Remember, your figure does not cross an asymptote, and that's true on this one here. So how do I construct these diagonal lines? The diagonal lines always go through the corner of your box, and they always go through the center of your hyperbola. Alrighty? So I'm going to go ahead and just make a note of that right there. And there is an equation for those, and if you want to look it up in your book, go for it. I'm not going to make you memorize those because you can figure those out just by plotting your points for the co-vertices, your vertices, and so on and so forth. Okay, so make sure you know these three equations, and we're going to look at a few examples of how to graph these in just a second.